I spent 37 years of my career working for BBC Research as a research engineer. That's 37 years in the ivory tower, not being let out. Just occasionally they throw you buckets of fish and things like that just to keep you happy. But in the last 2 or 3 years of that, I was the formal link between research and BBC production, getting HDTV going. This was in the late 90s. 2004, I retired, and I thought I was going to have a quiet life. How wrong I was. Since then, I've been busier than ever before, and particularly this project, something which I picked up 2 years ago and made a run, has kept me almost without sleep for 2 years. Fortunately, we are really now right at the end of it, in that the formal documents that I'm going to talk about are being edited on the final edit today before going to the EBU's technical committee to be approved. So we have a standard. Getting LED right for TV, that's the title we've got here. It's a bit of a misnomer because it's really nothing to do with LEDs. This is about lighting in general. Any lighting, I don't care what it is. The problem is, if you buy a light source and you are going to use it, how do you know it's any good? Can you tell it's any good? What do you do about it? The manufacturers, if they're reasonably honest, will publish a figure called the colour rendering index, the CRI, which has a scale of 0 to 100. But in real terms, there's nothing ever scores below 25, nothing ever scores above 80. And the CRI was developed in 1964 for the assessment of lighting to be used in offices and shops. So it tests for desaturated pastel colours using the colour science of the 1960s. We have moved on a little since then. We've got colour television for a start. But remember, this was developed right at the beginning of colour television, and the CRI makes no mention of television and covers none of the special odd aspects of television. But I'm going to. Thanks to work by these two guys, Bill Sproson and Bill Taylor, in 1970, they started work on a television lighting consistency index, which you just heard a short introduction to. This was a method of measuring light sources to see how their colour performance worked. It wasn't really to provide a direct measurement of how the colours worked, how the light sources worked, but how well they would match to each other if you used lighting mixed. Because at that time, 1970, we were just starting to see fluorescence coming into use in TV and arc lights. Prior to that, everything had been either tungsten or daylight. It's a nice smooth spectrum. Everything worked. That's how TV and film grew up, tungsten and daylight. But thanks to these two guys, we've moved on. And here's the problem. Television and film grew up with saturation grids. Wonderful. You can do what you like with a saturation grid. All the lights were tungsten. They go up and down, they move around, you put filters in them, you can dim them all. Okay, the colour changes as you dim them, so what? Everybody got used to it. But they cost an arm and a leg to run. Well, the problem is each of those lights dangling from the grid is effectively a dustbin with an electric fire in it. The electric fires consume an awful lot of power and give out a little heat. No, a little light. Sorry, to get this right, and an awful lot of heat. Think of an electric light bulb as an electric fire that gives out heat, around 7 lumens per watt. Lumen is an amount of light. If you look at those meter needles, that's the sort of power level that a studio would normally run at. Several hundreds of kilowatts. I've known of one studio using 400 kilowatts of lighting just for a blue cyc. There has to be a cheaper way to do it, because if you put all that energy into a studio, you've also got to get rid of the heat that you're not using for light, so you need the air conditioning. If you can increase the efficiency, everything gets better. Fortunately, we can. These are 10 kilowatt bulbs that the film industry used. I found them lying around at Pinewood. I couldn't resist taking a picture. The problem is, if you go to new type lighting, you'll find that lights are not what you think they are. This is an illustration of a Macbeth chart, which is a colour rendition chart. You've seen Jonathan holding one up. There's a new one in here. And that's lit by real daylight and a set of LEDs. 3 LEDs, a red, a green and a blue, balanced to produce the same white. You can see they're the same white because the colours along the bottom. The grayscale are all correct, these colours. That is split as well. So the grayscale's right, it's white balanced, the gamma is right, it's just the colour rendering that's wrong. So how is it so wrong? And could you attempt to put it right? Look at the guy's face on the right. I challenge anybody to put that right and keep the white balance right. This is almost impossible. So how do we quantify this? There has to be a way to do it. Fortunately, there is. This is what the two Bills, Bill Sprouse and Bill Taylor, invented. What they decided was we will have a set of test samples, which in their case was going to be the colour checker chart, but they did try 2 other sets of samples first. And you compare your test source with a reference source, and you put the resulting colours into a mathematical camera. This is not a real camera, it's one that we've designed in mathematics. So we need to define what the camera is. So we have a set of capture curves, matrix, gamma correction, and then the RGB picture signals go into a mathematical display. So we need to characterise that as well. So we need to know the gamma and the display primaries. That then delivers these numbers, X, Y, and Z. Whoops. X, Y, and Z, which go into a difference calculation in exactly the same way as the CRI does. But the CRI omits all of this television stuff. And the advantage is that since we're starting in the 21st century, we can use 21st century colour science rather than mid-20th century. So we can get it better. But we have done. And here's the result. Oh, by the way, halfway down this signal chain, you get access to the RGB signals, so we can see the pictures on TV as well. We can see this for real. I'm going to take my life in both hands now and run the software. There we go. This is stuff I've been writing for the last 2 years, because about this time in 2010 I was asked by a manufacturer, I won't say which one, to measure a new light that was coming onto the market. I measured its power output, its polar diagram, its lifetime on batteries, and then I was appalled at how bad the CRI was at measuring the colour performance. So I thought there has to be something better. Fortunately, I remembered this work which had been started by Bill Sprouse and Bill Taylor and finished in 1988, and then forgotten about because nobody adopted it, and thought, why not? I dug out all the research papers, worked out what they'd done, and thought, this is a bit primitive, we can do better. So I've written software that does do better, and here it is. Let's have a look at what actually happens. This is actually a light source I measured about an hour ago on a stand over there. And that's how well it does. Interesting thing is the spectral power distribution, which is what Jonathan was talking about, has a nice big blue spike here, and then a big dip, and then this big curve in amber. This is the blue end of the spectrum, that's the red end. So this in the middle here around 550 is green. The reason why it's got this weird shape is because that's the cheap way to do it. The LED that you see, coming back to this one, where all the LEDs are white, it isn't really white, it's a blue LED which is throwing energy into a layer of a chemical called a phosphor, which is exactly the same sort of material as you have inside fluorescent tubes, inside plasma displays to make the coloured light, inside cathode ray tubes. It's the same principle. You throw energy at the phosphor and it produces energy at a lower wavelength. So what's happening is that the blue wavelength, the blue energy at around 465, about 455, 460 nanometers, is pumping this phosphor to produce an amber light. But the amber phosphor is not intercepting all of the blue, so what you're seeing is the blue spike and the amber together, which balance together to produce a white. But the colour performance is rubbish because of the big hole in the middle. That big hole in the middle is caused by an effect called the Stokes Transmission. 19th century English physicist was looking at the process of phosphorescence, and he discovered that there's a gap in the transfer of the photons from one state to another. They jump literally from one state to another. It is this transition that produces a gap in the wavelengths. So, stating it another way, the charge pump, this big blue spike, cannot overlap the output of the amber. There has to be a gap in between. The fact that it doesn't reach zero is because energy from this part of the blue spike, the really deep blue, is still charging it, but energy from this end isn't. So this side is steeper than that side. Okay, so what do we do about it? Mix them up, use lots of LEDs, that's what we do about it. Let's go and have a look and see what we've got, because I've actually measured, I think, 79 different LEDs. Let's find one that works. Oh yeah, that'll do. Kelvin tile. Measured this around getting on a year and a half ago. You can see there the colour performance is better. Look in each patch, you'll see the outer patch is as lit by the reference colour, which is D56, and the middle is as lit by the Kelvin tile when set to D56. But you can see from the spectral distribution over here that there's a nice big blue spike, so we know they're using the same idea of a big blue LED lighting a phosphor, but added into the mixture there is a green, an amber and a red LED. So this is a 4 or 5 or even 6 colour mixture. The more light sources you have, the more you can fill in the gaps. And you can see that there's an LED here filling in the Stokes gap. So we can get better performance. And we can produce a number up here, TLCI number of 77 on a scale of 0 to 100. What we're saying is that anything above 50, a colorist can put right, because the colorists we've talked to said they can. So I'm not making this up, they made it up. If it's above 75, they can put it right easily. If it's above 85, they don't need to put it right. If it's below 50, they might be able to put it right, but it will be hard, expensive, and take a long time, and the result might not look very good anyway, because they will inevitably keying in some colours to try and put right specific colours rather than the entire scene. So anything scoring above 50 is going to do quite well. And I can tell you this scores about 30. So do any LEDs which are only 2 colour. So if you look at the light source itself, and you can see the individual LEDs, and there are white LEDs and yellow LEDs, it's not going to perform any better than this does, because there's nothing filling in the gap. Isn't this interesting? There's more. If I look at the down, here we go. At IBC this year, I went to IBC last year and read a paper on this, and we did another paper this year on the development of the standard camera. We went round various lighting stands on the Saturday with my measurement kit, which consists of this laptop and this spectral radiometer, asking if we could measure light sources. Fortunately, nobody said no, so we measured loads, which is where a lot of these measurements came from. By the Monday, the end of IBC, the manufacturers were coming to the EBU stand asking us if we would measure their lights for them. So I think, yes, we've made it. We've actually penetrated the system. We've actually made this work. But you can see this light source scores 93, which is really rather good. And you're actually going to be quite hard-pressed to see any differences within any of those patches. Can anybody see differences? I can, but only just. So above 90, forget it. It's fine. Everything works. And the reason is because this nice big blue spike is offset by a very long response here into the very far red. So the spectrum is being much better filled. This is a set of LEDs which are lighting up a set of phosphors which are not inherent in the device. In this, the layer of phosphor is bound inside the LED, so it's a single device. Two wires, put current through it, and that's what you get. In this device, the true colour, there's a set of LEDs in a panel, then there's a layer of phosphor in a plastic sheet, which looks like a filter. And you can slide different ones in, so you can get any colour temperature you like without dialing in numbers. You just slide the whole thing in. So all the riggers are going to love them because they look just like filters. Brilliant, nice and easy to work. And you would not believe the look on the girl's face when she came to the stand for us to measure these, and I told her how good they were. I've never seen anybody's eyes light up and glitter before, but hers did. And they were still glittering an hour later when she came back with her boss. But there are some rogues. There are also some rather good stuff. Let's have a look at the... Yes, here we go. Sorry to name this, but he didn't reply to his email, so he deserves what he gets. This was a small ring light, lots of different LEDs, got 6 different colour LEDs in it, so you should be able to get it right. But he not only didn't get the colour temperature right, he didn't get the colour mixture right either. You can see there's a big hole, big deep hole down here, all the way across green. He's got a red LED, an amber one, there's a green one in here which isn't lit, and there's a medium blue as well as this dark blue. Had he had access to this software and a measuring system before he came to IBC, he could have got this right, because it's only a matter of turning up the power to the individual LEDs, and he would have been scoring a good 90 instead of 72. So this is an aid to the manufacturers as well as to us. Does anybody get the idea that there's something in this and this might be useful? All right, good. I'm glad I'm not wasting my time then. To show you how all this came about, I'm going to take you into another dialogue. This is the thing that controls all the mathematics of it. Here we specify the light source, and this is what we're going to compare it with. It doesn't have to be the colour temperature. We can enter anything, so we can actually compare any 2 light sources with each other. I'm going to leave it on auto CCT anyway. The colour check, we've got several different sets of colour samples. Those 3, for instance, the colour check is the obvious one to use. The camera sensitivity curves, now that's interesting. In 1970, there were only Plumbicon TV tubes around. So the mathematics that Bill Taylor and Bill Sproson used was for Plumbicon tube. By 1988, we were starting to get CCDs, but they hadn't adopted CCDs into the curves. Now we've got CMOS as well, and there aren't any tubes left, so we should be using more modern measurements from more modern cameras. Let's see what happens if we do. This is a plot of the measurement values for something, I think it's something very like this. It's a thing that I used to call cheap Chinese 112 LEDs. Cheap because it was, Chinese because it came from China, it didn't have a manufacturer's name, and 112 because there were 112 LEDs in it. What else am I going to call it? So I measured the performance in delta E star is a measure of the colour differences that I've produced overall for the 5 different sets of camera tubes for which I'd got measures, this lot, for the 3 different sets of CCDs that I'd got, and for all of the film stocks that I've got measurements of. And there's less than a 2-to-1 variance between them. So we can say that it doesn't really make a lot of difference which set of camera tubes you use, or if you go and use film. So whatever we do for TV is going to work for film as well. That shouldn't come as a big surprise, because all the TV cameras and films have got to do the same job. They analyse the scene to discover what colours are in it in order to paint those colours on the display. That's the function of the camera. It hasn't got anything else to do. So the curves ought to look all the same. To work out what these new curves should be, a friend of mine in Oslo, a guy called Per Bøhler, he's the chief scientist, principal scientist in NRK. Lovely guy, he's a few months older than me, and he's still got another 6 months to work. I retired 8 years ago, so they're doing something wrong in Oslo. He dug out all the kit that he built in the early 1970s to measure cameras. Early 1970s is before the PC, so this is all hand-driven. There are no computers involved. And that's what the coffee cup's for. Because this is hard work, it takes a long, long time. The kit consists of this. Whoops, no, go back. Come on, that'll do. Yeah, this box is a lamp house. There's a light bulb in it. It's supposed to be a calibrated light bulb, but it's very difficult to keep light bulbs calibrated, so it's just a light bulb. This grey box here is a thing called a monochromator. It's a thing that makes light monochromatic, single wavelength. It's a grating that is swiveled around, and it actually produces a rainbow, and you intercept different parts of the rainbow in the output slit, so you produce a single coloured light, which is the green patch here. The camera looks at the green patch, makes that picture, which makes that parade waveform, RGB. So he knows the wavelength of the light, because the monochromator tells him that. He knows the value of the RGB, he knows the amplitude of the RGB signals, and he knows what the amplitude of the colour is, because this little bit here that's intercepted, you can see it clearly up here, is a photodiode that's sitting in the output port measuring the light level, and that's the bit that's calibrated. Incidentally, would anybody like to explain what's wrong with that picture? Oh, come on. Here we've got green light, but that says red is higher than green and blue is at 0, and so does the picture up there. Per doesn't understand this and can't remember how it happened. I think he must have been playing a recording from the camera. That's the only thing I can think of, because I can't think of any mechanism in any camera that could possibly do that. But it's just part of the fun. This is what science is about. And this is the sort of lab I worked in for 37 years, except mine was painted black with no windows. It was wonderful. That's the set of curves we came up with. Per measured 9 different types of camera from 4 manufacturers. Some of the cameras he measured several different bodies to make sure he got them right, and every camera was measured at least 3 times. So there's an awful lot of curves. But they all overlay each other beautifully. So clearly the manufacturers know what they're doing. Up to a point. Look at the difference in the red response out here. This camera goes on up to 740 nanometers, which is far red. This one stops at 705. There are subtle differences between the camera manufacturers. The crossover points as well. This camera has a crossover at 578 nanometers. This is at about 570. That changes the color rendering of the individual cameras very slightly in ways which I don't fully understand. But what it means is, once you've optimized a matrix for each individual camera, in theory you will not get the same results, so you can't match cameras together. In practice you can if you know exactly what you're doing, and I have been paid considerable amounts of money for doing exactly that, and I'm quite good at it. So I'm going to carry on doing that as long as people pay me to do it. So we took this set of curves and averaged them into this lot. It's been smoothed by hand. So there are some of the little crinkles and coggles on the previous data set that I've taken out simply because they don't make sense. They may or may not have been really happening, but this is a nice smooth set that we can believe. The green, I keep doing that. The green curve is broader than we would expect it to be, and the top is flatter. We would normally expect that curve to carry on up there like so. It doesn't, I think, because all of the manufacturers have decided they can make their cameras more sensitive by making the green curve wider. Allows more light into the green part of the sensor. Also, this bit along the bottom, where the red has a response underneath the green and the blue, improves the color rendering in CMOS cameras unbelievably. This is something I had not expected. It's a big, big surprise that some of the single sensor CMOS cameras have such good color rendering because of this long red response under the green. It makes life so much easier. We measured the different values, color values, that the individual color samples of the color checker chart would give for different values of display gamma. Now historically, NTSC believes that the TV display gamma is 2.2. PAL in Europe says it's 2.8. And the ITU says it's 2.4. They're all wrong. In the 1990s, I measured 26, 27 different grade 1 CRT monitors and got a value of 2.35 plus or minus 0.05. I've since found out why the older measurements were wrong. They were interpreting the maths wrongly. But you know, that's research. That's what you do. That's what I do anyway, and it's fun. But what you can see is it hardly makes any difference, particularly if you take the average, this black line. It doesn't matter what value you set the display gamma to. So if I say it's 2.35, or should be, and the ITU says 2.4, okay, fine, I'll take 2.4, I don't care. It doesn't change the difference, doesn't change the results. But this is the thing that really is the killer. How does the Television Lighting Consistency Index, TLCI, compare with the CRI, Color Rendering Index? Remembering that TLCI is based around the mathematics of a fully working TV system, and the CRI isn't. This is what's called a scatter diagram, and oh boy, is it scattered. This is 79 measurements that I made, all of the measurements that you saw in the table of files that I was selecting from. Horizontal axis is the color rendering index for each value. Vertical axis is the lighting television index. There is almost no correlation whatever. The results are different. That's not to say that the CRI is wrong. It's just that the TLCI is right for TV. And that's really as far as we can go legally. I could say the CRI is rubbish. And I've got a very strong suspicion that the CIE who invented it would very much like the CRI to curl up and die and go away, because it's over 50 years old, and it's about time it got updated. They have updated it twice, and each time all they've done is correct the spelling mistakes in the documents. So it looks like there is going to be no improvement on this at all. So please forget the CRI. It is not relevant to what we do. It will give you misleading results, and anyone quoting CRI as being important to television is telling you a fairy story. It really isn't true. If this diagram doesn't convince you, the next one should. Oh, no. I've left it out. Never mind. Let's end the show and go back to the software. Because this can do all sorts of interesting things. Most of the things it does are not available in the user version of the software. This software will be available for free through the EBU. A monochromator like this, a spectral radiometer like this, is only 700 Canadian dollars. This is not an expensive operation. Had I tried to do this 15 years ago, that box would have cost me at least 10,000 sterling. I can now do the whole thing for 500 sterling, plus a laptop. Let's show you some of the things that are actually under the bonnet. What we do when we take a light source is for every colour in the test sequence, these are the colours, 1 to 24 in the Macbeth chart. There's the name of the colour, and in these columns, these 3 columns, this delta E star is a measure of the lightness difference. Call it luminance. This is a measure of the chroma difference, call it saturation. And this is hue, which is colour, tint around the circle. A difference of 1, says the CIE, is just visible. So if we take the RMS value of these, which is take the square each value, sum, and then take the square root, we get a delta E star value, and that's the rounded up figure that we're actually going to use. So a value of 1 in this column is just visible. So these errors, the foliage is exactly 1. I've never seen that happen before. So we take each of these values and we make a Q value from them, which is the value we're actually going to use at the output. But we're not going to use the CRI really ridiculous formula. We've got a new formula for that. So as a color scientist, that is all I need. That I don't need to see the pictures. I don't need to see anything else. Just those numbers tell me everything I need to know about the light. But it's an awfully useful to see, as a colour scientist, to see something like this, which is a chromaticity diagram on the right. So each purple blob is where a colour should be when it's lit by the reference illuminant, and the cyan blob is where it's lit by the test illuminant. So you can see here that all of the reds, magentas are desaturated. They all point towards the white. This yellow is correct. These greens are desaturated, but the skin tones have a wrong hue. So we can't put this right with grayscale, we know that. We can't put it right with the hue shift. We can't put it right with the saturation shift. We have to put right every colour singly. And here is the bit that does that. Not the numbers listing. That one. You see, in this little table, I've divided the hue sector into 12 30-degree sectors, starting from red all the way around. And in each column, we give some advice to the colorist on what he has to do. A naught means leave it alone, plus means add some, minus means take some out. So using the number of pluses and minuses in these, the colorist gets a good idea on what he has to do before he actually has to do it. So you can assess a light in the shop before you hire it to work out how much work it's going to be to put it right in post. Does that sound useful? Good. Where are we? Yes, so all of these useful things get into the main report itself. So you get the colorist report top right, exactly the same. You get a pictorial show of the of the spectral distributions, which tells you what it's all about. This shows you what the colors are like, and you can have this either 601 coded so it looks right on the TV monitor, or sRGB so it looks right on the computer. So you can actually export that into color software and try and put it right, and you get told what the numbers are, what's not to like. I can go on like this for about 3 weeks. I'm not going to, because it's nearly 5:30. What I'm going to say is, anybody got any questions? Yeah. The next step, what's the next step? Good question, right. I started work on this November 2010. I spent the next 1 year rummaging, measuring, writing software, and the last year talking to the EBU and the SMPTE, getting everything standardized. So we now have 3 documents, 3 EBU tech documents which describe how it works. One is the methodology itself, one is the measurement campaign we run on cameras, and the third is a set of subjective tests we ran to decide which of the various options made the most sense. And boy, oh boy, was that fascinating. I could talk for a week on that, just that part. There's also a recommendation, R137. The final edits for those 4 documents are being done today in the EBU. They will be adopted by the EBU Technical Committee without further modification. We know that, sometime within the next couple of weeks. They then become an EBU standard. So the EBU recommendation says, if you want to measure lights, measure it this way. That's all it says. And the 3 documents, one is, this is how you make the measurements and present the results, and the other 2 are the support documents, which is how we came to derive that. So the next thing we have to do within the EBU is to publish a set of guidelines on how you use it, what it all means, so how long you should leave a light switched on before you measure, what the viewing angle should be, distances, that sort of thing. We have yet to start on that, but it's all common sense. There's nothing hard in that. That's just straightforward measurement science. That will happen as a background task. The other thing that will happen is the EBU has already decided to set up a workshop, probably after the production technologies seminar in February. So we're talking maybe March, April. It might be at somewhere like ARI in Middlesex, or it might be in Geneva. We don't know yet. It depends who is prepared to put up the facilities and make it all available. At that, we will have people like me, Jonathan Harrison, John Rossetti, Alan Birmingham, all the people from the EBU that we've been dealing with, plus as many lights as we can get together. We'll have a measurement campaign and a hands-on, this is how it works session. Does that sound useful? That's what's planned next. After that, God knows. After that, maybe I'd really do retire, because I've been retired nearly 8 years, and it would be nice to have a rest. Anything else?
How is this affecting the manufacturers?
Ooh.
How they're reacting?
Yeah. Yeah, how is this affecting the manufacturers? Yeah, what a good question that is. I got back to IBC. And before IBC, I'd been just simply talking to manufacturers. I mean, people like David and whatever, David Amflet. I've been going around saying, please can I measure your lights? And I'd gone to 24/7 in Teddington and had a go there. I measured stuff that I've got, which is why I've got so many different measurements. And all that is data used to make the algorithm work. So at IBC, we were going around to the stands asking for permission to measure lights. By the end, the manufacturers were coming to us asking for their lights to be measured. Some of the manufacturers went away very happy. Some went away very puzzled, Some went away very disappointed. Nobody has said we're doing it wrong. So I think the manufacturers have already taken this on. Is that right, David? Yeah, it is.
So we should see
Yes. Yes, we should see the lighting getting better, or you should see the proof that you get what you pay for. If a light's cheap, it's because it is cheap. Anything else? Yes. Yeah. Exactly. Yes. That's right. Yeah. So it's really a matter of how much control you're going to put in to the manufacturer, not just of the devices themselves, but the control of the devices. Because, for example, if you have a multiple LED like this one, where quite clearly there is a big red spike here, if you change the brightness by changing the current through the LEDs, you'll change the wavelength of this red. Now that changes the color performance. So the more expensive luminaires compensate for that by changing the amount of the drive depending on the temperature. So which means that the drive current into an LED will change with time, but the output will stay the same. This is not easy. It's not rocket science, but it isn't easy, and not easy has to get paid for. You really do get what you pay for. Anything else? No? Good. I can go home. Yeah, one more. You can always nail me afterwards. I won't be disappearing instantly, but I'm emailable, and I'm certainly happy to talk about this to anybody until the hind leg drops off the donkey. Thank you.